Well, hey there, it's Dr. Franklin, and I'm so excited that you elected to join me today. Today, I'm going to talk about hypothesis testing. And hypothesis testing is a statistical method that uses sample data to evaluate a hypothesis about a population. Said in another way, hypothesis testing uses sample data to draw inferences or conclusions about a population of interest. For example, in very simple terms, the logic underlying the hypothesis testing procedure is as follows. First, you state a hypothesis about a population. Usually the hypothesis concerns the value of a population parameter. For example, I might hypothesize that Sunni Muslims will lose an average of 10 pounds during the month of Ramadan. Step two deals with the following. Before I select a sample, I use the hypothesis to predict the characteristics that the sample should have. For example, if we predict that the average weight loss for Sunni Muslims is around 10 pounds, then we should predict that our sample should have a mean around 10 pounds. Now, important thing to keep in mind is that the sample should be similar to the population, but you always expect a certain amount of error. Step three deals with obtaining a random sample from the population. For example, this could involve me going out into the Hampton Roads community and selecting a sample of 200 Sunni Muslims and measuring the average weight loss that has occurred for them during the month of Ramadan. And then step four, finally, I compare the obtained sample data with the prediction that was made from the hypothesis. If the sample mean is consistent with the prediction, I conclude that the hypothesis is reasonable. But if there's a big discrepancy between the data and the prediction, then I decide that the hypothesis is wrong. Now, it's important to keep in mind that depending on the type of research and the type of data, the details of the hypothesis test change from one research study to another. For example, within our discussion here, we're going to be focusing on z-scores, but hypothesis testing can also involve t-test, ANOVAs, correlational methods, and statistics assessing sample proportions and comparing them to population proportions. Now, given that we've talked about that, let's move forward and lay out the four steps of hypothesis testing. All right, so hypothesis testing. Step one deals with stating the hypotheses. Notice that I said hypotheses. I said hypotheses because you'll be stating two hypotheses. One is called the null hypothesis. The other is called the alternative hypothesis. So this one is called the null hypothesis. I'm identifying it with a capital H and a subscript of 0. It's identified with a subscript of 0 because it is also called the zero effect hypothesis. And it basically means that the treatment has no effect. The alternative hypothesis is identified by a capital H with the subscript of 1. It's the alt hypothesis, and it generally says that the treatment has an effect. So the researcher is looking to disprove this hypothesis, and most researchers are looking to garner support for this hypothesis. Now, in order for us to see this in action, let me provide you an example. Previous research indicates that men rate women who are wearing red as more attractive than women who are wearing other colors. Researchers have come along and they wanted to understand how this would actually play out in a restaurant setting when waitresses wore red. Specifically, they were interested in if men would actually tip waitresses wearing red more than they would tip waitresses that are wearing a variety of different colors. So let's say that a researcher went around to several restaurants, gathered statistics from these restaurants on the average amount of tipping behavior seen, and they were sure to make sure that the restaurant waitresses were wearing a variety of colors. Let's say that the population mean or the average tipping behavior of men was 16% of their bill. And let's say the population standard deviation is 3 percentage points. So on average, most of the men are tipping about 3 points away from 16%. So we have some population parameters there or population statistics. Now let's say that the researcher went back to these same restaurants and he encouraged all the waitresses to wear red on a particular day, and then he gauged the behavior of 36 male patrons and monitored their tipping behavior over time. Afterwards, he calculated an average to see what their tipping behavior was like. So let's say the mean is 17.2. Okay, and that's the average amount of tipping behavior seen in the 36 gentlemen that were subjected to waitresses that were wearing red. In this particular research context, the independent variable is red attire, and the dependent variable is tipping behavior. How do we know this is the IV? This is what is being manipulated. It can be thought of as the cause. It's manipulated. Manipulated in that the researcher is manipulating the situation. They're manipulating the people. They're saying, hey, you wear this red shirt. Do this in this restaurant. Okay. And then afterwards, they're looking at tipping behavior to see if that red attire is affecting it. So if the IV is the cause, then we can think of the tipping behavior as being, you guessed it, the effect. Now, how would you actually write out your null hypothesis and your alternative hypothesis? I'm so glad that you asked. The null hypothesis would be written out like this. Population mean would be equal to 16%. We got a capital H, subscript of O, population mean equal to 16%. What this is saying is that even with the manipulation of the red attire, okay, the average tipping behavior is not going to change. It's going to stay at 16%. Now, the alternative hypothesis will look like this. See that equal sign with the slash through it? And we have 16%. So it's saying that the population mean will not be 16% once we get these beautiful waitresses in red attire, or these handsome waiters in red attire, and we assess tipping behavior. Now, this type of alternative hypothesis simply says that there will be a difference. There will be some type of effect. But there are instances where the researcher can specify a direction of the effect. So in other words, the researcher could elect to say that tipping behavior is going to be significantly higher than 16%, or the researcher could elect to say that tipping behavior is going to be significantly lower than 16%. These are called directional hypotheses because they indicate a direction. They're specifying a significant increase or a significant decrease. So there'll be other videos that will cover directional hypotheses, but for now, let's just focus on a significant difference relationship. In other words, let's just focus on the fact that after the manipulation of the IV, there will be some change expected in the DV. We're not specifying if it will be higher or lower, but there will be some change. Just looking at the sample statistical information, we can speculate that it's going to be higher. But remember, hypotheses are usually generated before statistical data is collected. Now, guys, step two deals with evaluating the credibility of the null hypothesis. You evaluate the credibility by formalizing the decision process and using the null hypothesis to predict the kind of sample mean that ought to be attained. For example, the null hypothesis states that the red shirt has no effect and the population mean is 16%. If this is true, then the sample mean should have a value around 16. Therefore, a sample mean near 16 is consistent with the null hypothesis. You'd accept it. On the other hand, a sample mean that is very different from 16 is not consistent with the null hypothesis. So with that understanding, the sampling distribution of the means can be broken up into two different sections. You could have one section identifying sample means that have a high probability if the null hypothesis is true, and then sample means that have a low probability of occurring if the null hypothesis is true. So in the tails, we have extreme scores or anomalies, and these are scores that have an extremely low probability of occurring if the null hypothesis is true. And this is present on the right side and on the left side of the distribution. Now keep in mind that if we were doing a directional test, we would just be looking at one particular tail. But in this case, remember, we're just saying that the treatment is going to have a significant impact, but we're not specifying the direction. So we're not saying extremely high or extremely low. We're just open to whatever the data will tell us. So if these are extremely low probability samples, if the null is true, then everything in the center is high probability values if the null is true. In other words, if we get a sample mean that is falling very close to our population mean and standard deviations, then it is very likely that our null hypothesis is true. If the sample mean is falling out in the tails, then there is an extreme likelihood that our null hypothesis is false. And it's a high likelihood that it's false because it's, again, way out in the tails. And the tails represent extremely low probability places if the null hypothesis is actually true. So, put another way, you can think of the tails as regions of rejection for the null, and you can think of the center of the distribution as regions of acceptance for the null. So if the apple doesn't fall far from the tree, then it's probably because the apple is like the tree. The apple doesn't fall far from the tree, it's probably because the son or daughter is like their parent. If the sample mean or the raw score doesn't fall far from the center, then it's very likely that the raw score, the sample mean, is from that population and the treatment isn't having an effect. However, if it falls way out here, then it's likely that this null hypothesis is indeed wrong. Okay, and that perhaps this hypothesis is true and the independent variable is having a significant effect. Now, ultimately, we have to set the criteria for decision making, and this is accomplished by selecting a specific probability value, which is known as the level of significance or the alpha level. So the alpha level is a probability value that is used to define the concept of very unlikely in a hypothesis test. The alpha level, said another way, is a small probability that is used to identify the low probability samples. By convention, commonly used alpha levels are alpha 0.05, alpha 0.01, and alpha 0.001. So for example, with alpha 0.05, we separate the most unlikely 5% of the sample means, the extreme values, from the most likely 95% of the sample means, the central values. What does that mean exactly? In other words, it means that we'll take that 5%, and in regard to a two-tailed test or a test where we're just looking to see if there's a difference, we'll put 2%, 2.5% in this tail, and we'll put 2.5% in this tail. And the extremely unlikely values, as defined by the alpha level, make up what is called the critical region. And the critical region is composed of the extreme sample values that are very unlikely, as defined by the alpha level, to be obtained if the null hypothesis is true. The boundaries for the critical region are determined by the alpha level. If the sample data fall in the critical region, the null hypothesis is rejected. So again, ultimately, you'll be coming back to these hypotheses and making a decision about accepting or rejecting them. And you will do so based on whether or not your sample mean falls into the tails of your distribution as it pertains to your problem. Now, many of you guys may be wondering, all right, well, how do I ultimately make that decision based on the information that I calculate within my research example? I'm glad that you asked. Well, in z-score values, plus or minus 1.96 would be the critical region boundary marker here. We have plus 1.96 there. We have negative 1.96 here. Okay. What that basically means is that if you calculate a z-score for this sample mean and it exceeds that 1.96 on the positive end or on the negative end, then that's grounds to say that that sample mean is statistically different, significantly different from the population mean of 16%, and you should reject the null hypothesis and accept the research hypothesis. Let me give you the other critical region boundary marker z-scores for other percentages. So for 0.01, it is plus or minus 2.58, and then for 0.001, it is plus or minus 3.30. Now, remember, if you're dealing with a two-tailed test, what that means is you're taking that 1% and you're breaking it up into two tails. So you'll have 0.005% right here. You'll have 0.005% right here. And plus 2.58 would be your boundary marker up here. Plus negative 2.58 would be your boundary marker down here. Okay, same thing with 0.001. Okay, you would take 0.0005 and put it in each of the tails so that when you add it up, it would be 0.001 in decimal format. Okay, we got a 5% alpha level here. We're breaking that up, 2.5% here, 2.5% over there. Okay, and then collectively it's 5%. All right, let's go to our unit normal table and look up these z's so that you can see in the tails how they equate to these broken up alpha levels. All right, so we're talking about z-scores in the context of critical region boundary markers, and I want to take a second to look up each of the critical region boundary markers that I've given you for the alphas so that you can see the percentages that are in the tails for each critical region boundary marker. So let's start with plus or minus 1.96. You know that unit normal tables do not have negative z-scores, so we're going to take the absolute value, the 1.96, and look that up in our first column. And from there, we will go over to column C, which identifies proportion in the tail. So we will find 1.96 on our far left column. And if we look up column C associated with 1.96, you will find 0.0250. If we were to multiply that tail proportion by 2, you would end up with 0.05, or the 5% probability that is representative of scores and values that are extremely unlikely if the null hypothesis is true. Now let's look up plus or minus 2.58 that is related to the alpha level of 0.01. On 2.58, look up column C, we find that there is 0.0049. Now, if we were to multiply that by 2, we would end up with something very close to 0.01, okay, which represents the 1% probability of obtaining values that are extremely unlikely if the null hypothesis is true. Finally, let's look up 3.30. Should be on the same page, and it is. In the tails of 3.30, we have 0.0005. Multiply that by 2, you would end up with 0.001. So that's the 0.001 probability in decimal format that a sample mean is extremely unlikely if the null hypothesis is true. So essentially, going back to our whiteboards, when we obtain z-scores that exceed these critical region boundary markers, we will reject the null hypothesis. It's important that I make sure that my wording is correct. When I talk about exceeding these critical region boundary markers, I'm talking about the absolute value. So it can exceed the critical region boundary marker on the positive end in terms of the signage and the actual numeric. But when you get on the negative end, what I mean by exceed is that if you get a negative z-score, calculated that is, it has to be negative 1.97, negative 1.98, negative 2.50 in order for you to reject the null hypothesis. All right, folks, so we are finally on to step 3. I've gone ahead and erased the whiteboard. I've erased everything but the critical region boundary marker that we're utilizing, which is plus or minus 1.96. Remember, if we get a calculated z that exceeds this 1.96 on the high end or on the low end in terms of the absolute value, we are rejecting our null hypothesis and in turn saying that the research hypothesis is true. Now we're talking about z-scores and we're working with a sample mean, so this is the formula that we'll be utilizing. We have a sample mean minus the population mean over the standard error of the mean. If you're not sure how this formula came to be and how it compares to other z-score formulas, please go and check out some of my previous content. on YouTube. So for now, let's just go ahead and plug in the statistics that we have so that we can get a calculated Z. So we have 17.2 minus 16 over a standard error of the mean. We need to calculate the standard error of the mean first. Standard error of the mean is population standard deviation over the square root of n. For our sample, that means square root of 36 over 3%. We take the square root of 36, we get 6. We put 3 in the numerator, and then we transform that fraction into a decimal, and we end up with 0.50. Take that 0.50, plug it there, because that's where it needs to be. 17.2 minus 16 gives us 1.2 over 0.50, and once we do 0.50 out, we end up with a 2.40. Okay, and this is positive. So step 3 is just computing the statistic, excuse me. Step 4 involves you making a decision about your hypothesis. So remember that the null was population mean equals 16%. Research hypothesis was no, it's going to be different once we manipulate that independent variable. Now, in terms of our critical region boundary marker, we said that plus 1.96 involves 2.5% up here. Negative 1.96 is right there, and it involves 2.5% this way. Now, we have positive 2.40, positive z-scores over here, negative z-scores over here, which means that our 2.40 likely falls somewhere out here. Okay, which basically means that this 17.2 is a sample mean that is extremely unlikely if the null hypothesis is true. Now, in more layman terms, this is a region of rejection of the null, and likewise over here, region of rejection for the null. This is acceptance of the null. So, given that we have a sample mean that's fallen right there, it stands to reason that we are going to reject the null hypothesis and accept the research hypothesis. Now keep in mind in making a decision, if you reject the null hypothesis, that means by default you are accepting the research hypothesis. If you accept the null hypothesis, that means that you are rejecting the research hypothesis. Keep that in mind, okay? So when you make a decision for the null hypothesis, in a way, you're already making a decision for the research hypothesis, okay? So this video has gone on long enough, but I hope that it has been helpful and that it has helped you to conceptualize what hypothesis testing is all about. We will be utilizing these same 4 steps moving forward as we talk about other statistics. So once you get a handle on hypothesis testing as laid out in our current chapter, you're going to be set, and there's going to be a higher likelihood that you'll be able to ascertain the new statistical procedures that we'll be talking about. I hope that this was helpful, and I hope to hear from you soon. Take care.